Hi there, my name's Aaron Lancherman. I'm a professor of electrical and computer engineering at Georgia Tech, and I would like to welcome you to ECE3084 Signals and Systems. This is the summer 2020 offering. Today we're going to prove a property about Laplace transforms having to do with integration, and we'll use that to find some Laplace transforms of things like ramp functions. So all these properties have a similar structure. We assume that we know the Laplace transform big X of some time function little x of t. And in this case, what we want to do is take our function x and integrate it. Here I'm going to integrate from 0 minus. Here we're telling ourselves to make sure we include any singularities at the origin to a t, and I'm using tau here as the dummy variable to make sure we don't get that mixed up with t. Don't worry, this tau here has nothing to do with convolution. It's just another thing that looks like t. So the technique we're going to use here is similar to the property we proved earlier that said that a shift in time corresponds to multiplying by e to the minus st in the Laplace domain. Namely, we're just going to take the thing we want to take the Laplace transform of and directly insert it into the Laplace transform integral. This is taking the place of what we would usually call x of t, the way we usually state the integral, and we're integrating against e to the minus st over time with the lower limit starting at this 0 that includes any singularities at 0 because we're always using unilateral, aka one-sided Laplace transforms. So the way I've always seen this tackled is with integration by parts. That's usually generically phrased like the integral of u dv is equal to uv minus the integral of v du. So now I need to pick the u and the v. It will be very convenient to let our integral here be u, because now by the fundamental theorem of calculus, knowing that integrals and derivatives are opposite operations of each other, du is just x evaluated at this upper limit t. And technically this is a differential instead of a derivative, so I need to put a dt here. So that means that this latter part of the integral here, that is our dv. So that means that v is the integral of this, which is just e to the minus st divided by minus s. Okay, so let's substitute these particular choices into this expression. We'll have u, which is this full integral here, times v minus the integral of v du, and I need to put in these specific limits here. So this bit in the front needs to be evaluated at the origin and at infinity, and the integral here is going from that origin to infinity. Okay, let me make the t here look something more like an actual letter t than a smudge. There we go, that looks better. So let's think about what happens to this first case. Well, if I put in the lower limit here of 0, then nothing's included in the integral, and that's going to give us 0. So we don't need to worry about that. What about t going to infinity? This is a little trickier. This is where a region of convergence issue would show up if we were doing bilateral transforms and needed to worry about regions of convergence. But here, to even talk about taking this Laplace transform at all, we're going to assume that s is such that basically this function here is not expanding faster than this exponential is contracting. So we're assuming this e to the minus st as t goes to infinity is doing what we want it to do and keeping anything that's growing here in check. So with that assumption, we'll assume that as t goes to infinity, this whole thing goes to 0. But again, a more careful treatment would worry about the details of things like that. This will be close enough to design MP3 players and nuclear reactors. So then the last thing that happens here is these minus signs will cancel. I'm left with an s that appears in front. And then what is left? Well, if you look at this whole mess here, not including that minus s in the denominator there, well, this is just a Laplace transform of little x. So we can just write a big X of s. So that was a whole lot of work just to come up here to say that if we integrate in the time domain, we divide by s in the Laplace domain. In all of the years that I've taught this course, I don't recall ever actually showing this integration by parts proof of this formula in class. I've always just presented this property as fact. Another way to think about it would be to remember this convolution property that we've used quite a bit. I haven't explicitly proved it, but it's true. That says that convolving in time corresponds to multiplication in the Laplace domain. If I were to take our x of t and convolve it with u of t, so here I'm plugging in u of t for h here in this property, I would have x of s times 1 over s in the Laplace domain, because 1 over s is the Laplace transform of our unit step function. And then if we remember that convolving with the unit step function corresponds to integrating that function, where here again I'm using tau to avoid confusion with the t variable. Now this minus infinity, we can get rid of that if we're living in the realm of one-sided, aka unilateral Laplace transforms. We're assuming that x of t is 0 for t less than 0. So this is just another way of thinking about the same property.